everybody, these are recorded. So here it goes. So for everybody that's joining. So today is number 5, where we're doing metals. We had to separate it from iron and manganese simply because we did a lot of the iron manganese last week. When we're working with arsenic, we're still going after co-precipitation. So we're going to be touching some of that when we're working with arsenic and iron and manganese. For those of you, if this is your first time, welcome. Should we get this lined up? And for those of you that are not familiar with AWC, we design and manufacture water treatment plants. We're out of British Columbia, Canada. So that's on the west side, on the Pacific side, just outside of Vancouver. We've been doing this now for over 40 years. We have close to 600 plants worldwide, and we manufacture everything in-house. So some of the things that we work on, which of course we'll be covering as to how this applies, we separate things in packages with the potable water, wastewater, and packaged solutions. When we're going with uranium plants, arsenic and uranium treatment, we're primarily going to be focusing on some of the packaged systems, meaning pressure filters, reverse osmosis, and ultrafiltration. And we'll get into it here in a bit as to why we have to do this, okay? Okay, so let's get started. So yes, the dreaded periodic table. Of course, I know not everybody likes to see this, but again, with water, we're either trying to add something to our water, removing something from our water, and it all falls down to chemistry. So last week, we made sure that we covered iron and manganese, and this time we're going to be going after arsenic and uranium. Iron and manganese are primarily an aesthetic objective, where arsenic and uranium is actually, they're poisonous. So it's actually toxicity levels through it. And of course, that also applies to cadmium, mercury, lead, and chromium. So what is arsenic? One of the things that makes arsenic very unique is that it's, other than it's a poison, yes, it's a semi-metallic element. What this means is it's also found as an organic form of arsenic. So you can't always say that arsenic is only found in metals. I'm sure you've heard about apple juice. And apple seeds. Yes, there are very trace amounts of arsenic in apple seeds, which is the same thing applies to apple. And it's not the metallic form, but rather the organic form. So some of the poisonous elements of arsenic, of course, include nerve damage, bladder, lung, skin cancer. And the kidney and liver cancer, believe it or not, is actually something that's coming up a little bit more. And on the skin cancer front, we'll cover that in a minute because there's a difference between trivalent and pentavalent, and one will affect the liver more than it will do skin cancer. So we'll cover that on the different forms of whether we're working with a trivalent or a pentavalent. So we have talked about this before, but I just want to make sure we're going to be bouncing around some of the terms as to what we're using. So MCL is a maximum contamination level that's used by the US EPA in the US. MAC is what's used in Canada for maximum acceptable concentration, and AO is aesthetic objective. Of course, when it comes to arsenic and uranium, there is no aesthetic objective. It is primarily going to be falling under MCL and MAC. The quick calculator that we go over is 1 part per million equals 1 milligram per liter, and 1 part per billion equals 1 microgram per liter. When we're treating for iron and for arsenic and for uranium, we're going to be using the ppb, or the parts per billion, or micrograms per liter. So this is how you're going to see it reflected. Okay. When you're doing with metals, other metals, say iron, manganese, and other parameters, we're going to be using ppm. In this case, we're going to go down to the parts per billion. If you want to understand what parts per billion looks like, just picture a pile of M&Ms that you have 1 billion M&Ms. Okay, so billion M&Ms, that's a whole lot of them. And 1 part per billion is exactly that. That is 1 part per billion in that big bucket of M&Ms. So these are the set standards. Oh, uranium should show up there too. These are the set standards that were set by both the Canadian Health Standard and the US EPA, and it was also added on to the World Health Organization for arsenic and for uranium. MCL is 0.01 parts per million, or 10 parts per billion. We're going to be using that, the ppb, and of course in MAC it follows the same, also 10 ppb. Uranium, interestingly enough, the MCL set by the US EPA is set at 30 parts per billion. That's in the US, and while the World Health Organization and in Canada, we're using MAC of 20 parts per billion. Interesting about the arsenic, and I don't know that I have another slide on this, is that arsenic used to be set at 50 parts per billion back in the 80s. That was actually set by the World Health Organization, and it wasn't until the US EPA went and did some specific research on it that back in 2000 and I want to say 2006, don't quote me on that, I think it was 2004, 2006, they came up with a specific standard of 10 parts per billion, and the 10 parts per billion is what's being used now across the board. And the World Health Organization went in there and used 10 parts per billion as their new threshold as well. So let's start with arsenic. So we primarily find arsenic in two forms. And again, we're focusing on water. We're not going to go into oil, soil samples or food. Okay, so primarily water. Yes, this is a water course. So arsenic is found in two forms. We have trivalent arsenic and pentavalent arsenic, also shown up as arsenic 3 or arsenic 5. It's pretty easy to remember. Tri equals 3, penta equals 5. So trivalent arsenic is what's known as undissolved, or basically it's a dissolved form of arsenic, while pentavalent is an oxidized form, kind of what we did last week when we touched iron and manganese, where we had a ferric oxide versus a ferrous oxide. So trivalent arsenic, again, more on the dissolved side, is found in deep wells, a high pH environment, a reduced environment, high pH, and where hydrogen sulfide is present. You don't always have to test for what's known as a speciation to understand whether you're treating for trivalent versus pentavalent. You know that if it's a deeper well, you're going to be finding arsenic 3. High pH, you're also going to have arsenic 3. And the second you have hydrogen sulfide, it's a very clear indicator that you're working under arsenic 3. I apologize if I bounce around between trivalent arsenic and arsenic 3. It's the same thing. Okay. Now, when you've got a shallower well or a lake where you've got arsenic, it's going to be primarily pentavalent, meaning that it has been somewhat oxidized, much like ferrous and ferric iron. Now, you're going to find it in shallow wells, surface water, say lakes and rivers, and you'll primarily find it with higher levels of iron and manganese. Why do you find it with higher levels of iron and manganese? You have the ferrous iron that has precipitated to ferric iron, which will co-precipitate with your pentavalent, meaning when you find any kind of iron in your water or other metals in the water, it means that the arsenic has already precipitated and it's already now in pentavalent form. So why is it so important to identify the two? When it comes to your health or the toxicity element to both different kinds of arsenic, when we're dealing with trivalent arsenic, because of course it's a dissolved form of arsenic, it can be inhaled and ingested and of course dermal absorption. It is also 60 times more toxic, and it needs to be oxidized in order to be properly removed. Now, a lot of people say, well, if arsenic is in the water and I'm not drinking it, then I'm fine, I can still shower it. Okay, true. However, when it's trivalent arsenic, you have dermal absorption, and it can also be inhaled. So this is something that if you're in your shower, because it's a dissolved form, any vapors that are coming through the shower, you can actually inhale it. Interesting enough, which is unlike what you would find in other metals. Okay, once we go into a pentavalent arsenic, you can potentially inhale it, and of course there's ingestion. Dermal absorption is to a lesser degree. Like we mentioned, that it also causes skin cancer. So you will find a lesser degree of dermal absorption through pentavalent arsenic because it's a larger particle, and it can be reduced with reverse osmosis. And something I guess I should have put on the left column, trivalent arsenic cannot be removed by reverse osmosis to a significant degree. Can it be somewhat removed and reduced by about 30 to 40%? It can. However, not a significant amount of reduction with reverse osmosis. Unfortunately, part of the industry has said, you have arsenic, throw a reverse osmosis into it and you're done. However, it depends on what kind of arsenic you have. Hi, Jeremy, how are you? So we are going to take a quick look at where we're finding arsenic. So this is a project that we were doing in Canada, in northern BC. We were primarily treating for about 65 parts per billion or micrograms per liter arsenic. As you can see, these are just samples that were tested. We're trying to stay below 10 parts per billion. Now, interesting enough about arsenic, and we'll take a look at some more maps that I identified, it comes in clusters. So basically means that if you ever have an arsenic, if you ever have somebody that has tested positive for arsenic, you can go anywhere between a 5 to 10 mile radius, then you will always find arsenic to some degree in water. This particular case was a project we were working up with a Indian band, a First Nations band in northern BC. You'll see some hot pockets of it, of course, in the southern BC, of course, and also Alberta, Manitoba, Ontario, and Quebec. Now, interesting note, a lot of labs will only flag arsenic when they hit 10 parts per billion or over. Sometimes you'll see water reports that are coming in at 8 or 9 parts per billion, and it doesn't mean that it's safe to drink. Just because your arsenic levels are 8 or 9 parts per billion and they're below the threshold, it doesn't mean that it shouldn't be considered whenever you're putting in some kind of water treatment. So here is the US. So this was something that was supplied by the US Geological Survey, and it was done by primarily for soil. So you're going to see that it's not parts per billion, but parts per million. And now we're ranging anywhere between 5 to up to 700 parts per million. Okay, remember the conversion rate? So if we're doing, say, 8 parts per million, that comes out to 8,000 parts per billion. And we know that the standard, the MCL standard, is 10. So it's pretty high. Of course, soil sampling and water will leach out arsenic. So wherever you're going to find arsenic in your soil is where you're going to have arsenic in your water. I worked on a very specific article on how water gets leached out of, how arsenic gets leached out of arsenic in your soil. So this is a clear reflection of what this would look like on the other end. So let's go back real quick to one slide. So again, this is what arsenic looks like in your soil. And then when we come over to our water table, it comes like this. And there is also a temperature element to it. If you're going into, and it's not only temperature, you're going to see here that anywhere between 10 to parts per billion. We've got clusters in western Texas. We've got California. I've done some projects in Colorado, and you'll see here that on the coast of Wisconsin, upstate New York, there's also significant parts of arsenic. And interesting enough, for those of you that are calling in from Canada, I know that we're a big group today. Up in Fort Mac, they had relatively lower levels of arsenic. And then 2 or 3 years ago, they had the big fires that basically burnt down something like 80% of the city. Well, after that, they started testing what their water tables were looking like, and their arsenic levels came up. There was a specific article and some research that was done that was primarily done to see how temperature reflects and speeds up the leaching process of arsenic in our soil going into our water tables. And this also applies in California. When the water tables were dropping in California and we had not only hotter temperatures, but also our water tables started dropping during the drought, we also had some levels of arsenic that started reflecting in our water. So this is a quick little summary from the Canadian Water Guideline that talks about arsenic. So, and this applies across the board, it's not just in Canada, and the World Health Organization publishes too. There is no safe level associated with arsenic. Sorry guys, a couple people are logging in. Hi Casey, thank you for coming in. So there is no safe level, okay? They are trying to find something that can be as low as reasonable achievable, which is the ALARA method, which is something that the US EPA uses as well. So don't be fooled by saying I've got 9 parts per billion or 12 parts per billion and you're within a safe amount. Again, it's as low as reasonably achievable. I don't know if somebody logged in and hasn't muted the mics, if everybody can please mute their mic. So it's all based on the limitations, and that's where the 10 parts per billion number was set, okay? So we're going to go a little bit as to what what arsenic does for both dermal absorption and some of the extremities. Arsenic inhibits the way oxygen goes through your body, so it affects your extremities a little bit more. There are some images here that might be disturbing, so those of you will go through them. We won't spend too much time on them. Okay, so this was known as Blackfoot disease. This was done, and it was a very specific paper that was done on people that were exposed to arsenic for extended period of time. As you can see, it affects the way oxygen gets distributed through your body. So on the left-hand side, you're going to have skin cancer, and on the right-hand side, believe it or not, that's not cancer. It's just the lack of oxygen that you're getting to your extremities. The same thing applies to here. This was something that was done in, I want to say this was Vietnam or India. No, next one's India. This one's Vietnam. This was something that was done in Vietnam. And again, you'll see that it's the way it affects how your body is transmitting oxygen through your bloodstream. And so it's going to be affecting a lot of your extremities. Necks and hands and feet are one of the most ones that get affected the most. Here's another one. So this was one that was particularly somebody that was exposed up to about 10 years drinking 50 parts per billion of arsenic contaminated water. This is actually where the health organization, I'm going to switch that slide, it bugs me too. Okay, this is where the World Health Organization officially changed their MCL levels, because they had been preaching that 50 parts per billion was the accepted amount for decades, since the 60s. And there was this research that was done in Bangladesh and in India that were primarily showing that, yes, you can be exposed to 50 parts per billion arsenic, and that's what you get. So yes, absolutely not the safe levels. So how do we treat arsenic? So we've mentioned there's a few ways of treatment. We primarily focus, we've got adsorption, ion exchange, and membranes, okay? So these are kind of, there's pros and cons to every single form of treatment, like there is with any technology. So with absorption, you have what's known as full bonding. Absorption, you're primarily using either activated alumina or titanium dioxide. I'm not a fan of activated alumina because you need very specific pH conditions, and then you can potentially leach out the aluminum into the water. Titanium dioxide is what we recommend because it binds onto your arsenic. The same thing applies to uranium. So you've got higher removal rates. You've got some pretty good calculations as far as media. It is sacrificial media, which means that it needs to be replaced over time. And there's faster kinetics, which means that you've got pretty fast contact time. So now we move on to ion exchange. I'm going to keep these pretty short because just being respectful for everyone's time. With ion exchange, it does a great job. It's selective, which basically means it will only go after negatively charged ions that primarily fall under arsenic. It is a selective media. However, it needs regeneration. And what regeneration basically means is that you're going to have a high concentration of arsenic that needs to go down the drain, or rather it needs to go somewhere. And when we say it needs to go somewhere, primarily it goes down the drain. So of course, there's going to be some very specific regulations as to how much arsenic you can be dumping. If you're treating for 80 parts per billion, you're reducing it by 95 to 97%. Well, the arsenic has to go somewhere when you backwash. The same thing applies to the membranes. Membranes can achieve about 90% reduction when we're dealing with pentavalent arsenic, which, like I mentioned, it's already oxidized and precipitated arsenic. However, when it goes to trivalent, best case scenario, you're looking at about 40 to 60%. It's just not the right way, or it's just not the right solution or the right technology. And again, the concentrated discharge, where are you putting that water? California came up with some very specific guidelines where you cannot use reverse osmosis to treat for arsenic. So that is an absolutely no. So can you treat arsenic with some forms of reverse osmosis? You can. However, you're now discharging a very high concentration, which can make it back into the water source. Now, of course, like all technologies, there's also some fouling issues. So whenever you have metals in water, you're always going to be interfering with the absorption portion of it because it focuses on metals with titanium dioxide. With ion exchange, you also have fouling with organics and sulfates because it is a negatively charged ion. When we go into membranes, we're going to have the same issues we have with all membranes, right? So potentially iron, organics, or sulfates, or even high TDS can interfere with how our membranes are performing. Okay, so we're just going to cover those three. We can go a little bit more into it, and if you have any questions on any specific applications, please let me know. So this is what we do with what's known as co-precipitation. So this is what you're going to be doing with whether you're working with membrane solutions, ion exchange solutions, or when we're going with adsorption. So we use a catalyst media to do what's known as co-precipitation. The way co-precipitation works, and we've covered this extensively last week, was we're oxidizing two metals to work together. Now there's a very specific ratio that happens when you're trying to co-precipitate two metals. So of course, we work with a catalyst media here. We've got green sand, phyllox, pyralox, and catalox. I've mentioned I'm not the biggest favor on the green sand. But if you have a certain amount, the rule of thumb is about 20 parts. So if you have 20 parts of iron or manganese to every part of arsenic, you can co-precipitate it to a certain degree. Meaning, if you have 15 parts per billion arsenic and you have 2 parts per million iron, you can oxidize and precipitate out your your iron, knowing that it will create a ferric oxide, which will now bind to your arsenic. So that is, in fact, a way that you can treat it. Now, of course, there's some very specific considerations as far as pH. We touched on the importance of pH, and this is where pH and hydrogen sulfide is present. It's something that needs to be treated ahead of time. So this is kind of what an inlet and outlet arsenic concentration works with when we're dealing with adsorption, so using titanium dioxide. As you can see, there's some very specific empty bed contact times that need to be achieved in order to treat, but we're going here from 20 parts per billion in the range of 15 to 20 parts per billion down to pretty much non-detected or in the 1 to 2 parts per billion rated. And of course, these are total bed volumes. This is what a standard or a traditional arsenic filtration looks like. We have to do some pre-filtration. I apologize, that says green sand. We do some pre-filtration for any other metals, and we have arsenic if we're going to making sure that we treat arsenic with titanium dioxide. In this case, we are doing titanium dioxide. That is what a kind of a standard containered unit looks like. Again, we are using a green sand followed. This is a relatively small 200 gallon per minute unit, relatively small and compact, but of course you can go up to 800 or 1,000 gallons per minute when you're treating for arsenic. So how are we doing for time? Yeah, you see I mentioned that we were going to be running out of time. So we're going to jump into uranium real quick. I won't go into it too much because it's going to follow a very similar approach to treating for uranium. We still had adsorption for adsorption like titanium dioxide to treat it. We still have ion exchange for treating uranium, and we still have reverse osmosis. Interestingly enough, the MCL standard and the MAC standard for uranium is different in the US and Canada. So the US EPA pegged it at 30 parts per billion. Canada, we're a little bit more conservative, of course, and we used the maximum acceptable concentration of 20 parts per billion. Okay, so this is a direct reflection of what we have for soil samples. As you can see, soil samples, again, reflected in parts per million. We're dealing at anywhere, I mean, take a look at the US. You'd be surprised how prevalent uranium is in the US and the levels there are. Now, of course, this is soils only, but you can see that there's a clear reflection of uranium going into the water. So these are some of the samples that were tested. We're taking a look at anything. So in the orange to red, we're going from 20 to 30 parts per billion or micrograms per liter. This is comparing both uranium and nitrates. Now, as you can see, there is still a specific level of 30 parts per billion uranium, even in parts of the US. I've personally done some work in Colorado, in Nevada, and in upstate New York. Uranium falls into veins, basically means that wherever you find uranium, you're going to find it anywhere between a 5 to 10 mile radius. So as you follow the vein, you're still going to have uranium. That's kind of where it was being treated. In Canada, we have a province that actually went after it and did quite a bit of research for what their uranium levels were. This was a particular project that we're working up in Northwest Territories. So their range was anywhere between 51 parts per billion to 190 parts per billion. We pegged it at 92 parts per billion in order to treat it. And these are some of the projects that I've personally worked on in Canada where we're going through different levels of uranium treatment. Now, what makes uranium so hard to treat? Uranium decays over time, okay? And as it decays, it actually changes forms. Now, there's a certain decay of our uranium valences, they're known as isotopes, so it's not known as a valence. So uranium isotopes, as it breaks down, it changes into different parts. Now, as you can see, the breakdown or the decay of uranium, it'll break out into protactinium within 26 days, into actinium into 10 days, and some of them are taking in the tens or hundreds of thousands. Look at astatine and radon, right? So it's a relatively fast decay. So the tricky part of it is that you're not only treating for uranium on its own, you're actually treating some of the very specific breakouts of uranium. Some of them you have to worry about, some of them you don't. Some of them are in seconds and some of them are in the billions of years, like when you're going into bismuth. But you still have lead. Lead still is going to be leaching out or decaying at a relatively fast pace when you're looking at hours and any kind of stable form. So for most common forms of uranium decay, of course, you've got your alpha, your betas, and then you've got your inverse and isometrics. We're not going to be touching that at all today, but just gives you an idea of why you're basically chasing something that's constantly changing. And that's why you want to kind of pick up uranium at its core. Interesting enough, with uranium, we're using, again, titanium dioxide as adsorption media to absorb it in the US. And while it can handle some very high both flows and contact times as far as reduction, it's important that once you have the media that is depleted on the transportation side, You can't transport any kind of media that has certain levels of uranium unless it is considered now radioactive, and there's very specific regulations as how you transport it and dispose of it. So when you're sizing something for uranium reduction, you have to make sure that you size it and you do your estimated life cycle so that you don't actually have that breakthrough. You're primarily reaching about 60 to 70% capacity until the media needs to be disposed so that it doesn't have to be treated or stored as a radioactive material. So we'll just touch some of the pretreatment. This applies for both uranium and for arsenic. No, we're not using gravity filters to treat for uranium. We're treating it, however, as pretreatment. Okay. The reason why it's so important to pretreat is uranium is such a small molecule and it's unstable at that. You can't just throw something at it and treat for uranium. You need to make sure we're reducing turbidity. We need to reduce organics. We need to reduce metals and tannins. So there's a lot of pretreatment that needs to go after uranium. You can't just say we're going to treat for uranium without actually taking a look at a full comprehensive water report. This is an example of how we can treat for uranium. We are pegging a tube settler for turbidity and for organics, followed up with reverse osmosis. This particular one was not used for uranium, and I know that we've covered why we wouldn't use reverse osmosis for uranium. However, in some remote communities, you have no other choice, so you're using reverse osmosis to reduce uranium as much as possible. However, that's the way it should be done. So this is a pressure filter, and why do you need pressure filters to treat for uranium? The medias that you're using for uranium are primarily ion exchange and titanium dioxide. So again, it's an absorption membrane. They need pressure. They actually need pressure in order to be able to properly bind onto your media. So it can't be done through a gravity filter. The manufacturer, while we've asked for it and we've asked for data sheets from the manufacturer, which is Graver Technologies, they insist that it needs to be done through a pressure filter. We've kind of covered what pressure filters look like. These are some of our pressure filters. There's a lot of other pressure filters out there. You begin with an anthracite or a zeolite bed, so fine sand that can go down to about 30 microns after all pretreatment, and then we go through the actual media that we're using, whether it be ion exchange or whether we use a selective absorption media. So either way, this is how you lay it out. If you take a look at something like this, which I kind of used last time to use the same slide that I used last time for manganese, you can achieve some pretty high levels. Gary, if you're on the call, I think you are, we were working with a customer for doing a project up north where we were using this very similar layout for treating for arsenic. And if I remember correctly, we were running at about 600 gallons per minute. What makes unique about treating for both arsenic and uranium is that you can use what's known as lead lag. So anytime you're over 80 parts per billion arsenic, any kind of absorption media or ion exchange media has a hard time keeping up. So easy enough, what you do is, let's just say we're treating for 200 parts per billion arsenic. You start with stage number 1. You've got water going into stage number 1. We're achieving about 80 to 90% reduction. As our water's coming out, it's going to be coming out at about 20 to 30 parts per billion arsenic. And now we put in a second stage, what's known as lead lag, second stage in order to go ahead and treat for final polishing reduction. So we can easily go from 200. I've treated up to 800 parts per billion of arsenic and pretty high levels up to 120 parts per billion of uranium using a lead lag approach. And that's kind of what it looks like with the filters. And we're done. Oh man, look at that, 29 minutes. That was pretty close. I told you I was going to go over a little bit. So if we have any questions, I insist that anybody can put it in their chat box. I apologize that we kind of go through these so fast. The idea is to have a really information session on everything. I kind of like to call these bite-sized brownies. You're not going to learn all of it, but at least you can get enough information on how to begin treating or how to address arsenic and uranium. So does anybody have any questions for me? Don't be shy. You can go ahead and turn on your camera, or if you'd like to punch it into the chat box. Evan, I know you had a question for me last time and you didn't have enough time to put it in there. No? Okay. So one of the
don't have one this time.
You don't have one this time. Okay. So on the co-precipitation front, and this question comes out a lot, is we are co-precipitating even when we're using catalyst medias. We have to co-precipitate your arsenic with another metal. So you can't just go in and put in a catalyst media like any kind of green sand or manganese dioxide, like we mentioned, Pyralox, Phialox, etc. You can't just throw in a media and expect it to do all the work. You need to be able to co-precipitate it with another metal. So, well, everybody, thank you very much for joining us today. Next week, we're going to be doing ultraviolet disinfection. I promise it's going to be shorter, a little bit more compact, and a little bit easier, and zero chemistry, other than a little pre-treatment that we need to do. So thanks again for joining us. If you have any questions, there's my email. If you don't follow us already, make sure that you can follow us on LinkedIn. That's AWC Solutions. We are pretty active in the community, and we try to share more information there. So thank you, everybody, and see you next week. Oh, there is a chat box question. Okay, Diana. Okay, maybe no questions. They're primarily talking about electrochemical co-precipitation methods used commercially. There are electrochemical co-precipitation methods used. However, the co-precipitation primarily works around sulfates. So, and you can foul it up if you have any other organics. I don't know how much of the electro co-precipitation has been done for metals, so I couldn't answer that. But I do know that it's very effective for sulfates and nitrates and primarily positively charged ions. Remember that arsenic and uranium is a negatively charged ion, so the selection that you have to use is a little different. Okay, so thank you everybody for coming, and I will see you next week. Bye.